Hello, I'm Aditya Anugu, and this is the Spring Oscillation Lab. The goal of this lab is to analyze the motion of a simulated spring model attached to a mass as the mass moves in an arc, and the system oscillates vertically versus an experimental setup of this situation. We're interested in this problem because we can learn how certain factors like the spring constant and the mass attached to the spring impacts the motion of the spring mass system in the simulation, and we can compare this to the experimental data to see how accurate a model is. In this lab, we use Newton's momentum principle, which states F net is equal to the change in momentum over time, and then based on that, we can derive all of this. We also use the energy principle in this lab, which states that work is equal to the change in energy. Change in energy is 0 in this lab because no energy is lost, and change in energy would be change in kinetic, gravitational potential, and spring in this case. The next principle used in this lab is the energy principle. We know that work is equal to the change in energy, and in this case the change in energy is equal to the changes in kinetic plus gravitational potential plus change in spring potential, which equals 0, because none of the energy in the system is lost. Additionally, we know that change in kinetic energy is equal to kinetic final minus kinetic initial, which is equal to 1/2 m change in v squared. We know that change in gravitational potential energy is equal to gravitational final minus gravitational initial, which is also equal to mg times change in height. We also know that change in spring potential is equal to spring final minus spring initial, which is equal to 1/2 k times the amount that the spring is compressed or stretched squared. Here are some of the references used in the experiment. As you can see here is the actual video used for the experiment. If we let it play, we can see that the mass oscillates on a spring, and there is this calibration stick which measures this distance to be 0.7 meters. Then we can analyze the x position over time and the y position over time, and we'll notice that they move in sine and cosine-like patterns. And here's all the data outputted by Tracker. After putting the data from Tracker to an Excel file and converting it to a CSV, we can import it into our program in GlowScript, and then we can have a comparative model from our experiment versus a model. As you can see, we have the graphs here, and I'll show you shortly in our PowerPoint. And if we let the whole simulation run, it'll end up something like the pictures I'm about to show you. Over here you can see some of the calculations done to find certain values. Specifically, we found the coefficient for the spring constant, which is 6.88 kilograms meters per second squared. Then we also found the resting length of the spring, which is 0.128 meters. These are all the calculations here. You can pause if you want to look. Here's the code for the GlowScript program. The mass and the mass of the position vector are specified in the lines shown here, and then the calculated values for the spring constant and the resting length of the spring are shown here, as well as the equations for K, UG, US, and total E. Then we have the initial values for the energy specified, and the velocity of the ball is updated based on the net force found from Fg equals mg and Fs equals Ks. Then the position of the spring is updated as well according to the position of the mass. Then the final energies are calculated the same way the initial ones were, and then are subtracted by the initial energies to find the changes in kinetic, spring potential, gravitational potential, and total energy. Here are the results of the lab. Now what does it all mean? Total energy of the system stays constant, and as the spring stretches, the change in spring potential is positive and the opposite direction compared to when it's compressed and negative. Similarly, change in gravitational potential is positive when the spring is compressed due to an increase in height, and the change in gravitational potential energy is negative when the spring stretches out, and the spring potential energy is positive due to the mass being closer to the ground. And the change in kinetic energy depends on if the mass is speeding up or slowing down when you're observing it. The periods for oscillation on the x and y axis are different. For the x-axis, it's 1.709 seconds, and the y-axis, it's 1.52 seconds. This is a difference of 0.2 seconds, and this is because they have two different equations. In the x-axis, you have this one. The y-axis, it's this one. The x-axis depends on length and gravity, whereas the y depends on mass and spring constant.